Folks, Mr. Ackerman here. Thanks for watching. This is the supplementary video for Unit 5, Lesson 1, and the topic is momentum and impulse. So at this point, I'm going to assume that you've watched the instructional video, and now I'm going to take you through the lecture notes to show you what we would have done if we were together in class. So, getting into the lecture notes themselves, you'll see that we begin with a definition of this concept called momentum. And by now, you know that momentum is a vector quantity that's equal to the mass times the velocity of an object. And you've probably used the word momentum in your daily vocabulary, but maybe you didn't know exactly what it meant to a physicist. How is it different than something like speed or force or something like that? Well, we're going to find out. We start with a very basic example that I'm sure you can all do. You can check your solution against the solution manual when you're done. But I don't want to spend too much time on this page. I'd like to get into the more interesting stuff. So on the second page, you're going to see that there's a demo that we were going to do. And in order for you to see everything, I'm going to pull myself off to the side here. So the part that you have in your lecture notes just says a little demo to help us understand momentum, dropping 500 and 1,000 gram masses into our hands. And basically what was going to happen in class was I was going to have you guys pair up. So in the first demo, one of you would be sitting in a chair like this with your one hand out, and the other one would be standing up in front of you, holding both masses and getting ready to drop them. You would drop them one at a time, so the 500 gram mass from a certain height, delta H, into your hand, and then the 1,000 gram mass from the same height into your hand. And this works best if the person who's catching the mass has his or her eyes closed and doesn't know exactly when the mass is going to hit. And what I would have asked you to do was just basically be to try to catch the mass and try to record in your mind what it feels like to stop the mass. So you're going to be thinking, how much force did it hit me with, or how much force did it take me to stop it? And because you don't know when it's going to hit, you really get a good idea of what it feels like to experience a certain mass moving at a certain speed. Now they're both falling from the same height, so the speed is the same, but because the mass is different, they have a different momentum. And in class we were going to use 500 and 1,000 gram masses, so the momentum was going to be double for the heavier mass than it was for the lighter one. And you could really kind of ask yourself a question in a loose sort of way. Does it feel twice as hard to stop a mass that's moving at the same speed but it's twice as massive as a lighter one? And a lot of people agree that it's definitely harder. Whether they can decide in their minds that it's twice as hard or not is debatable, but it at least gives you the idea that we're going for here. Now, in the second demo, what we do is we drop the heavier mass from a certain height, maybe the same height as before, but then we drop the lighter one from a higher height. And the goal here is to make sure that this extra height gives us extra speed. And how much extra speed? Well, enough so that we have exactly the same amount of momentum. So if you think about this one here is going to impact with some velocity v. And if we calculate the momentum, we're going to get P equals mv. Now you can figure out that v by thinking along these lines. Eg goes to ek in this drop. But now we have half the mass, so let's call it m2 equals half of m1, and therefore when it hits, we need that v to be bigger than this v. So we want v2 to be 2 v1 so that the product mv is the same for both cases. Now how much higher do you have to drop the lighter mass from to get twice the speed? Well, again, if you do this, mgh to a half mv squared, and you think in terms of proportions, we want double the speed, so what do we need to do to the height? I'll give you a hint, it's not double the height, it's more than that, and you're going to have to work that out. But once you do that, you can ask your partner, so someone at home who's dropping this, to drop the different masses from the different heights, and you can catch them and decide whether they feel the same, because this time they're supposed to have the same momentum. So does it require the same amount of force from your hand to drop them? And I think in a lot of cases you'll find that they do. Now, I'm going to pull myself back in here so I can talk to you for a moment. I have two masses at home here that I took from school before they closed it up. One is a 200 gram and one is a 500 gram. So the ratio is 2.5 to 1, but you get the idea. You probably don't have these kinds of masses at home. I don't even know if you have a scale. So if you don't have something with a known ratio like that that you can measure, then think to yourself, what could you do to have masses that had a specific ratio? And I think if you look around your house, especially in the kitchen, you're going to find certain items that have their mass printed on them, and so you can answer the question. Maybe it's just going to come down to literally maybe you have a plastic container half full of water and then completely filled with water, and the rough 2-to-1 ratio is enough. Okay? So anyway, my point is you can try this demo at home, and I'm curious to know what you think about it. I'm going to pull myself up here for a sec to just review one other question that I want you to answer. What factors affect how hard the mass hits your hand? So when I say how hard, I mean if you're dropping something and it's like, ow, that really hurts. If you catch it like this, really without letting your hand move, kind of hurts. But if you give with it like this, it's a lot easier to catch it. There's less force required. It doesn't hurt as much. And that's what I'm talking about down here when I say what factors affect how hard the mass impacts your hand. I think you can probably guess, well, the distance over which I bring it to rest, and therefore the time over which I bring it to rest. In other words, the time has an effect on how much force we're going to feel. So let's take a look at that next. In here, you're going to see a familiar equation, F net equals ma, Newton's second law, and what we're going to do is we're going to work with this to derive a new formula. So acceleration, of course, is v2 minus v1 over delta t. And if you work that in there and you, of course, expand the bracket, you're going to get mv2, or mv final, minus mv1, mv initial, over time. And this, of course, is just momentum final minus momentum initial divided by time. And when we have final minus initial, that is delta, or a change. So we have a new version of Newton's second law, which tells us that the net force on an object is actually the time rate of change of its momentum. So how does this force increase? Well, if you change the momentum in a short time, small denominator. How does this force increase? If whatever time it takes, there's a lot of momentum to change. Like a car has a lot of momentum. No matter what time you take to stop it or change its momentum, that was a lot of force. But a baseball, much less. So this is known as the impulse equation, where impulse is the change in momentum, delta p. There's a question here for you to try, and read it carefully. Make sure you draw that all-important picture, and be careful about directions, because what are the directions here when they talk about the velocity? Well, that's important. Momentum is a vector quantity, and so you always have to be aware of that when you solve these. Give this one a try, and then check your solution in the solution manual to see that you got it right. Moving along, here's another demo that we were going to do in class, and also it's actually a video. The video is one of the videos that we saw earlier in the course, which are on VHS, believe it or not. I cannot find this online anywhere. It was just no one ever, I guess, pirated it and put it up. But anyway, I want to tell you what was in this video so that you can see the link with momentum. Picture a football, like in the American game of football, and picture two sticks of wood with a loose sheet. Could be a bed sheet or a towel or a sheet of canvas. It's held very loosely in there. And somebody throws the ball, which has mass m, with velocity v1, and it goes into the sheet rather. And if you can picture this sheet, it's very loose. So as the ball travels into it, the sheet just completely envelops this ball and it comes to rest. Now, they repeat the demonstration, same mass football, same velocity, but this time the sheet is pulled very, very tight between the two wooden posts here. Now, can you imagine what's going to happen? Well, you might imagine that the ball is going to hit the sheet and bounce off. So whatever it does, that's going to really exert a strong force on that sheet and the two wooden supports that are holding it up. And in the video, what happens is these wooden posts actually break, and that's meant to show that there's a lot of force. So if we bring this back to impulse, what we would have done in class is we would have said, okay, now F net, the net force on that ball, is equal to the change in momentum over the change in time. When you throw into a loose sheet, the ball is brought to rest, so V2 is 0. From V1, initial speed, down to 0, that's a certain change in momentum. But the time is very large, and therefore the denominator is big, and the force needed to stop that ball is pretty low. And that's why the frame, the wooden posts, don't break. But in the second one, where the ball comes to rest, but over a very short time period like that, we now have a small denominator. We got the same numerator, it's the same initial speed and the same final speed stopping the ball, and therefore that extra force is what causes the frame to break. In fact, what you actually see in the video is that the ball bounces backward. It doesn't stop the way it does when you have a loose sheet. And this is interesting. I want you to think about this for a minute. When something hits something hard and bounces back, you've taken its momentum from a vector quantity this way, not just to 0, but to a vector quantity that way. And that's a greater change than if the object just stops, the way it does when you catch something. So think about that. Something bouncing off has a greater impulse than if the exact same situation thing just comes to rest. And there's a question in your textbook that deals with a tactic used by riot police to control crowds without using lethal force. They're called rubber bullets, and as the name suggests, they are not made of metal, so hopefully they don't go into you and cause bleeding and extremely serious damage to your body. But also rubber suggests something bouncy about them, and in fact they are meant to bounce off of people. And so in that way, there's a greater transfer of momentum, which we're going to learn about in the next lesson, section 5.2. Keep that in mind because there is a question in the book that deals with this. I don't want to say too much more about it right now. There's a couple of other quick things to think about. A demo that we could have done in class if we were there. Imagine an egg. I don't have an egg with me right now, so this ball will have to be the egg. If you were going to drop an egg on the floor, what happens to it? It breaks. We all know that. It's like this up here. There's a sudden, quick change in momentum, small denominator, lots of force, egg cracks. But what if you put a pillow on the floor so that the fall is cushioned? In English, we say, oh, the fall was softened, the force was gentle. But in physics, we say, oh, well, when an egg falls into a pillow, it's like throwing a ball into a loose sheet. It basically increases the time and therefore decreases the force, and the egg doesn't break. And you can try this at home. Don't waste food if you can help it, but I guess you could sacrifice an egg to see what would happen, and I think you'll find that that's the case. Think about this. Imagine that you were jumping from some height onto the ground. What do you do with your legs? Do you land straight-legged like this? No, you bend your knees. Everyone knows to bend his or her knees because it's really painful. In fact, you can really damage your spine if you don't bend them. Even a little kid who's never taken physics before knows to bend his or her knees. What are these kids who've never taken physics doing? Well, their brain comes programmed with this formula in it. They know that if they don't increase the time, then they're going to increase the force. So go figure, even little children who can barely speak know that you have to cushion the blow, you have to increase the time in order to minimize the force. And so that brings me to the last part of the lesson here. It's a situation where you may be dealing with forces and changes in momentum. However, sometimes the force is not constant, and so plugging into this formula is not feasible. give you an example, something we just studied in the last unit, springs. If I take a spring and I stretch it, there's a variable force. It's getting harder and harder to stretch. And if this was a compressible spring, like the kind you see in a car in the suspension, that I can crush down like that, same thing. What about a baseball? When a baseball gets hit by the bat, or when a golf ball gets hit by the head of a golf club, what happens to it? There's a great little video I found here. I've been having trouble finding this on YouTube, so what I've done is I have found another similar example where what they do is they show you a golf club hitting a ball in slow motion. Just going to pull myself over here, and we're going to watch this together so you can see what the YouTube video is. And let's just play and watch what happens. Maybe you never knew, but I think this is kind of cool, that something as hard as a golf ball actually compresses noticeably when it's struck by the head of a golf club. Now, think about that for a minute, and think about a baseball getting smushed like that. Think of it like a spring that's not stretching, but rather compressing. And as you compress it, Kx is the force, right? X is increasing, Kx is increasing, the force is increasing. We got a variable force here. And therefore, what do we use in the force, in the impulse formula? What value? If the value is increasing and then decreasing, what do you use? Well, if you know the average value, you can use that. But often, it's hard to find the average. So what we do then is we use a new kind of graph, a force time graph, and underneath the force time graph, the area. How do we get area? We multiply by the base, which is down this way in seconds, and the height, which is in newtons. And that gives us impulse. So that's the idea here. You can find delta P by finding the area, and then, if you know the time, you can find the average force, and so on. And so that's it. Hope you enjoy this intro to momentum. We're going to get into much more interesting examples involving collisions, which is kind of what a lot of physics is based on, objects coming together and interacting. So stay tuned. That'll be our next lesson, 5.2. Hope you're staying safe. Bye for now. Thanks for watching.